All right, so today we're going to be talking about geometric probability. The theoretical probability of an event occurring is P, the number of outcomes in the event over the number of outcomes in the sample space. All right, so it's basically part over whole. This is something that you actually learned in previous years. I believe you learned it in Math 7, maybe even Math 6. So this first portion is 100% review. So let's do some examples before we begin. So if we look at length, if we're using length, like in this first example, it says a point is chosen randomly on AD. Find the probability that the point is on BD. All right, so the entire line is line AD, right? So that's going to go on the bottom. Whereas the part of that line would be BD. So that would go on the top. That's the number of outcomes in the event, and then the number of outcomes in the sample space would be the entire AD. So you're going to do, you're going to figure out what BD is. BD, if we look at this, BD is actually 10. So that's where they got this from. And then your AD, the entire segment, is going to be 2 plus 4 plus 6, that's 12. So then you would have 10 over 12. Now, if you simplify that, you'd end up with 5 over 6. Same thing if we're using angle measures. So it says use the spinner to find the probability of the pointer landing on the 160 degree space. So you're going to do, for the probability, you're going to find all of the points in the 160 degree region over the entire number of points, or all of the points in the circle. So part over whole. So you're going to do 160 over the entire circle, which we know that an entire circle is going to be 360 degrees. And if you weren't sure, you could just add up all of those angles and it will end up giving you 360 degrees. So you would do 160 over 360 and you would get 4/9. All right, so let's do some examples here. So for question 1, it says the point is on FH. So we're going to look at this entire segment, EH, right? So we're going to do FH over EH, right? So FH over EH. All right, so the distance of FH is 3. And then the distance of EH, the whole thing, would be 8. And you can't simplify that, so then my final answer here would be 3/8. So let's look at number 2. So it says the point is not on EF. So that means everything on here except for EF. So that means we want FG and we want GH, and we're going to, again, put that over the entire segment EH. So FG is 1, GH is 2, so you're going to add those up. That's going to give you 3. And then that's going to be over the entire segment, EH, which again is 8. So then you would get 3/8. So again, we did, so this was FG plus GH over the entire segment, EH. Okay, so that's what we did to find 3/8. All right, on example 3, it says the points on EF and GH. So EF and GH, or GH rather. So we have EF, that's 5, and then GH is 2. So when we add those up, that gives us 7. And then over the entire segment, 8. Moving on to question 4, it says the point is on EG. So EG, that has a distance of 6. So 6 over the entire segment, 8, and that does simplify to 3/4. All right, moving on to questions 5 through 8. On question 5, it says the pointer landing on 135. So we have 135 out of the entire circle, 360. So we would do 135 over 360, and then that would simplify to 3/8. On example 6, it says the pointer landing on 75. So again, 75 over the entire circle, part over whole, 360, and that simplifies to 5/24. Moving along, so it says the pointer landing on either 90 or 75. So now we have two different parts on here, right? So if we're looking at 90 or 75, we would add those up, right? So we're going to do 90 plus 75 over the total, or the whole circle, which is 360 degrees, okay? When we simplify this, we do end up with 11 over 24. All right, on example 8, it says the pointer landing on 30. So again, we're going to do the same thing. We're going to do part over whole, 30 over 360. And so then that simplifies to 1 over 12. All right, let's look at some actual geometric probability now. So before this, we were just looking at regular probability. Now we're going to look at geometric probability. And that's when we have like an area. So if we have a part of an area over the entire area. So like for this first example, we have a triangle within a rectangle, and they want to know what's the probability of a point that's chosen randomly inside the triangle, right? So if that was the case, then you would do the triangle, the area of the triangle, over the area of the rectangle, right? So the entire area would be the rectangle. That part that we're looking at is the triangle, so it would be part over whole. So first they found the area of the triangle, 1/2 base times height, so they did 1/2 times 6 times 3, and they got 9. And then for the area of the rectangle, base times height, so that's 10 times 5, that gives you 50. And then so for the probability, you're going to do the points on the triangle, so in other words, the area of the triangle over the points on the rectangle, in other words, the area of the rectangle, and then you're going to simplify. So when you simplify, you end up with 9 over 50. Sometimes they'll ask you to give it to them as a decimal. So if you were to convert that into a decimal, it would become 0.18. All right, so let's look at this first example here. So it says they want to find the probability of it landing, or of you choosing a point within the square. Okay, so we have a square within a rectangle. So we're going to find the area of the square first, and then we're going to find the area of the rectangle, and we're going to do the square over the rectangle. So the square, the area of the square is just 2 squared, which is 4, right? So 2 squared is 4. And then the area of the entire thing is 7 times 4, that's 28. So I have 4 over 28. I want us to round to the nearest hundredth, so when you do that, you get 0.14. All right, moving on to question 10. So we have a triangle within a rectangle, and they want to know the possibility of choosing a point within the triangle. So then the probability of this, you would do the triangle over the rectangle. So you're going to do 1/2 base times height for the triangle, right? So 1/2 times 5 times 12 over the area of the entire rectangle, which you would just do 14 times 13. When you put that in the calculator, you end up with 15 over 91, which simplifies to 0.16. They wanted us to round to the nearest hundredth, so then it would be 0.16. All right, moving on to the circle. So for the circle, they want us to find the probability of us choosing a point within the circle, right? So the circle out of the entire area of that entire rectangle. So in order to do that, you're going to find the area of the circle, which is pi r squared, right? So that's going to be 8 squared pi over the area of the rectangle, which is 16 times 22. So whenever you simplify this ends up simplifying to 2 over 11 pi. And then when you put that in the calculator and you round to the nearest hundredth, you get 0.57. Okay. Moving on to question 12. This one's a little bit harder because now we have a pentagon. We're going to have to find the apothem and all of that fun stuff. So in order to find the probability of you choosing a point within the pentagon, you're going to have to do the area of the pentagon over the area of the entire thing, which would be the rectangle. So I'm going to start off by finding the area of the pentagon. Before we can do anything, we need to figure out the central angle of a pentagon. in order to do that, I'm going to do 360 degrees divided by the number of sides, which in this case is 5, and that gives me 72, okay? So that means that each of these angles, each of these central angles is going to be 72 degrees. Now, in order to find the apothem, we know that the apothem is the distance from the center to the side. So one thing about the apothem is that it bisects the angle. So then these become 36 each. And then it also bisects the side. So then this is going to bisect this side length. So this is going to be 2, this is going to be 2. And so we are going to figure out the apothem, because remember, the area of any regular polygon is going to be 1/2 apothem times the perimeter, all right? So that's for the area of the pentagon. So in order to find the apothem, which is this, all right, which is that distance, you're going to have to use trigonometric ratios. So you're going to use, since we are given the opposite side of the 36, and we're also trying to find the adjacent side, the only trig function or the only trig ratio that uses the opposite and the adjacent would be tangent. So you would use tangent. So you're going to do tangent of 36 equals 2 over the apothem, 2 over a, right? So then I'm going to solve for a. I get a equals 2 over tangent of 36. Now, I'm going to keep that in exact form, because if you round first and then plug it in, your answers are going to be off. And even if it's off by 100th or 1/10, it's still going to be incorrect. So keep it in exact form until the very end. So the area is going to be 1/2 times my apothem, which is 2 over tangent 36, times the perimeter, which is just 4 times 5, right? And that's just going to be 20. Okay, so we have the area of the pentagon. Now to find the area of the rectangle, that's pretty easy. That's just going to be 10 times 8, and that gives you 80, all right? So now that you have all of that, you can find the probability of you choosing a point within the pentagon. So you're just going to do, for P, it's going to be 1/2 over tangent 36 times 20, and then that's all over 80, okay? So now this is what you're going to be plugging into the calculator. When you do that, you get a probability of approximately 0.34. Okay, now one thing that I want you guys to understand, sometimes they won't ask you if it'll land within the pentagon. Sometimes they'll ask you, what if it lands here? Okay, what if it lands in the shaded region? In this case, you're going to first find the area of the pentagon, and then in order to figure out this shaded region, or the probability of you choosing a point within that shaded region, you're going to actually need to take the area of the rectangle and then do the area of the rectangle minus the area of the pentagon to get this portion, and then put it over the total area, which is the area of the rectangle, right? So there will be times where we will ask you questions like that, and you really do need to understand how to do that. So again, if you're asked to find the shaded region, right, the probability of the shaded region, then you would, once again, you would do the rectangle minus the pentagon, and all of that over the entire area, which is the area of the rectangle, right? So let me just show you how that would be done. So in order to find the probability of the point within the shaded region, you would do the area of the entire rectangle, so 80, minus the area of the pentagon, which is 1/2 times 2 over tangent 36 times 20, and then all of that over the area of the entire rectangle, 80. So you will have questions like this on your test, so just make sure you understand how to do that.